In this lecture and in the coming lectures, we are going to talk about the running times of algorithms. So first of all, there are two crucial parameters of algorithms. First of all, memory complexity, which is the amount of memory the given algorithm needs. And because memory is quite cheap, this is why memory complexity is not that crucial. So this is why we have to talk about the running time complexity of an algorithm. The running time complexity of an algorithm defines how much time the given algorithm needs. And by the way, we will come to the conclusion that there is a trade-off between memory and running time, in the sense that if we can use more memory, then we can significantly reduce running time. On the other hand, if we want to save some memory, so we want to minimize the amount of memory the given algorithm needs, then the running time is going to be slower. So there's a trade-off between memory complexity and running time complexity. But usually memory is quite cheap, so this is why running time complexity is more crucial. Okay, so the problem is that we want to measure the running time of a given algorithm and we want to decide whether a given implementation is fast enough or not. So for example, if we are dealing with Dijkstra's shortest path algorithm, which means that we have an underlying graph with several vertices, in this case we have A, B, C, D, E, G and so on, these are the vertices. There are edges connecting these vertices and there are edge weights associated with every single edge weight, and the aim is to find the shortest path between a starting vertex and every other vertex of the graph. With the help of Dijkstra's algorithm, we can solve this shortest path problem. And let's assume that we run this algorithm on a smartphone. Smartphones are fast, but of course they are not as fast as powerful computers. So if we run the same algorithm, the exact same implementation on a computer, or for example a supercomputer, of course it is going to be way faster. So this is why we can come to the conclusion that measuring the running time of given algorithms is not going to be a good approach, because it depends on the underlying machine, whether we are using a smartphone, whether we are using a fast computer or so on. Okay, so this is not a good approach to measure the exact running time of algorithms. We should measure the number of steps instead. So the number of steps the algorithm requires with respect to the input size. So for example, when we are dealing with a graph, the number of vertices is the input size. If we are dealing with items we would like to sort, then of course the input size is the number of items we want to sort. So essentially, running time analysis is going to define the relationship between the number of steps and the input size. Of course, the larger the input, the more steps the algorithm requires. But anyways, this is the relationship we are going to analyze. You may pose the question that why is it a better approach? Because it is more generic, more flexible, and finally it is machine independent, and of course this is exactly what we want to end up with. Because of course the same implementation may be faster depending whether we run that given algorithm on a computer, on a smartphone and so on. So essentially we would like to avoid these inconsistencies. So this is why we are going to measure the number of steps the algorithm requires with respect to the input size. Don't worry, we are going to talk about it in the coming lectures. So for example, we have a one-dimensional array of integers and we want to construct an algorithm that's going to sort these integers. So we have 12, 4, -2, 1, 20, 0, 8 and 3, and of course the result of the algorithm is going to be the sorted order. For analyzing algorithms, we have to consider the number of items we are dealing with. This is the input size. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8 items, so the input size is equals to 8. And of course, we can measure the running time of the algorithm in milliseconds. For example, if we have a one-dimensional array with 10 random integers, then the sorting procedure takes 100 milliseconds. For example, we measure the running time of the algorithm when the underlying one-dimensional array contains 100 items, and we come to the conclusion that the algorithm takes 1000 milliseconds to finish. What's crucial that we want to know the algorithm's running time with respect to the number of items, so with respect to the input size. So we don't care about the running time in milliseconds. You may pose the question again, why? Because it is not machine independent. A smartphone is going to be slower than a supercomputer. So this is why measuring the running time in milliseconds makes no sense. We are after the running time with respect to the number of items. So essentially we are going to measure the number of operations the underlying algorithm has to do. By the way, this is called the order of growth. So how the algorithm scales and behaves with the n input size, where n is the number of items. So for example, we are going to implement several problems and we are going to pose the question that what's going to be the running time of the algorithm when we have a different array size. So essentially there are more items the algorithm has to sort. So we are going to talk about these problems later. What's crucial that instead of measuring the running time of the algorithms in milliseconds, we are going to measure the running time with respect to the number of items. This is called order of growth. Let's take a look at a concrete example. For example, the algorithm can do a specific operation on 10 items in 100 milliseconds, and the same algorithm can do the same operation on 100 items in 1000 milliseconds. What does it mean? You can see that we have multiplied the number of items by 10 and the running time has been multiplied by 10 as well, which means that the running time scales linearly with the input size. But of course, it may happen that the implementation, so the algorithm, is slower. What does it mean? That for example, the algorithm takes 100,000 milliseconds to finish with a given operation on 100 items. So what does it mean? That we have multiplied the items by 10, but the running time has been multiplied by 1000. So we can come to the conclusion that this is the so-called quadratic running time complexity. We are going to talk about it later, don't worry. The main problem with the second approach is that it doesn't scale well, and we want to make sure that the algorithm is not going to freeze our application. For example, we would like to search for a given person on Facebook. Of course, Facebook has several billions of users. You may guess that the search algorithm must be fast because otherwise we have to wait for minutes for the application to find the given user. And of course, it is not going to work fine. Facebook finds a given person in milliseconds, so it is working extremely fine because the underlying implementation, so the underlying algorithm, is extremely fast, which means that it scales well with the input size. If the algorithm doesn't scale well, then it means that it is slow, so we have to wait for the given operation to be finished. And of course, we like deterministic algorithms where the running times are approximately linear or sublinear. We are going to talk about it, don't worry. So in the next lecture, we are going to talk about a concrete example, and then we are going to talk about linear running time complexities, quadratic running time complexities, exponential running time complexities, and so on. What's important that instead of measuring the exact running time of algorithms, we are going to deal with the number of steps the algorithm requires with respect to the input size. Thanks for watching. In the previous lecture, we have been talking about the fundamental basics of running time analysis, and in this lecture, we are going to take a look at a concrete example. So for example, we have the first algorithm, and we measure the running times in milliseconds. So we come to the conclusion that sorting 10 items, so when the input size is 10, we will end up with 1 millisecond as the running time. If we have twice the size of the input, so we sort 20 items with the algorithm, then the running time is 2 milliseconds. So as you can see, double the input size, double the running time. If we have 100 items we would like to sort, then it can be done in 10 milliseconds. So 10 times the number of items, so 10 times the input size essentially, 10 times the running time. So we can come to the conclusion that this is a typical linear running time, which is denoted by ordo n. We are going to talk about it in the coming lectures. What's crucial that, as you can see, the running time scales linearly with the input. We have 10 times the input size and we end up with 10 times the running time, which means that it scales linearly. By the way, the exact values doesn't matter because of course the running time depends on the underlying machine. For example, the algorithm runs quite slowly on smartphones, but the same algorithm runs extremely fast on a supercomputer. So usually we don't care about the exact values, but we care about the relationship between the running times and the input size. So this is why it is a linear running time algorithm, which means that the running time scales linearly with the input size, which means that it is going to work fine. We like linear running time algorithms. What if we have the second algorithm and we come to the conclusion that sorting 10 items takes 1 millisecond, sorting twice as many items, so 20 items, is not going to take 2 milliseconds for the algorithm, but it takes 4 milliseconds. What does it mean? That we have twice the size, but we have 4 times the running time. What if we try to sort 100 items? Then we end up with 100 milliseconds. Of course, this is just for demonstration purposes. It is just an example, but as you can see, we can come to the conclusion that if we multiply the number of items by 10, so we have 10 times the input size, we are not going to end up with 10 times the running time, but we end up with 100 times the original running time. So this is why we can come to the conclusion that the running time of the algorithm scales quadratically with the input size. This is called ordo n squared. We are going to talk about it in the coming lectures, but what's crucial that if we compare the two algorithms, of course we prefer the first one, because the first algorithm scales linearly, while on the other hand the second algorithm scales quadratically, which means that we have to wait more for the second algorithm to do the sorting operation than with the first algorithm. So of course the first algorithm is better. We are going to take a look at several implementations and it is going to be clear. Usually, we are interested in large input sizes. This is called asymptotic analysis. So we will drop all the terms that grow slowly and only keep the ones that grow fast as the input size becomes larger. Anyways, in the coming lectures, we are going to talk about this big ordo notation and we will come to the conclusion that we don't care about the running time when the input size is equals to 10 or 100, because of course, as you may guess, that very slow algorithms are going to run extremely fast if the input size is 10 or 100. We are interested in cases when the input size becomes larger, such as 10 million items, 100 million items, and so on. This is when, for example, linear running time complexity is way better than quadratic running time complexity. So these are the topics we are going to talk about in the next lectures as well. Thanks for watching. In the previous lectures, we have been talking about the fundamental basics of complexity theory, and in this lecture we are going to talk about maybe the most important topic as far as big O notation is concerned. So first of all, what is the big O notation? By the way, this is called Landau notation as well. It describes the limiting behavior of a function when the argument tends towards a particular value or infinity. Usually, we are after very large values or infinity. This is exactly what we have been talking about in one of the previous lectures. This is called asymptotic analysis, that essentially we will drop all the terms that grow slowly and only keep the ones that grow fast as the input size becomes larger and larger. So essentially, we would like to have a good guess about the running time of an algorithm when the input size is large enough. Okay, so this is why we are after the limiting behavior of a function, and of course the function in complexity theory measures the running time complexity of an algorithm. The big O notation is used to classify algorithms by how they respond in their processing time, so the running time or working space requirements. This is what we have been talking about, that memory is quite cheap, so usually we are dealing with the processing time or the running time to changes in the input size. This is what we have been talking about earlier as well, that we would like to measure the relationship between the input size and the running time. Okay, so let's take a look at the mathematical definition. Let's assume that we have two functions. We have the f function that measures the running time of the given algorithm. Of course, we have the input size n, which is equals to big O of g of n. G is another function, and of course we are dealing with the input size as well. This expression means that there is some c constant, and c is greater than 0, and some n0 so-called threshold value, such that for n larger than n0, the absolute value of the function will be smaller or equals than the constant multiplied by the absolute value of the g function. So you may guess that it is quite complicated, but if we take a look at the illustration, essentially it is quite simple. So first of all, when n, so the input size, is small, then essentially we don't care whether the f function is greater or the g function is greater. So here, as you can see, sometimes the f function is larger than c times g of n, but sometimes the f function is smaller. But what's extremely crucial, that if n is larger than n0, so essentially on the right side of the illustration, we can see that the fn function is smaller than c multiplied by the g function. And this is the definition for the big O notation. So if we can find a c constant and the n0 threshold such that the fn function is smaller or equals than c multiplied by gn, this is when we can say that fn is equals to ordo gn. So essentially, ordo gn defines the upper bound for the fn function. So as you can see, this is the upper bound because we know for certain that after the threshold, when n is larger than n0, the fn function will be smaller than c times g of n. In the coming lectures, we are going to take a look at concrete examples, but let's talk a bit about bubble sort. Bubble sort has ordo n squared running time complexity. In this case, n squared is the g function. So as you can see, ordo g of n, we have a g function, and we know for certain that c multiplied by gn is going to be the upper bound for the running time. In this case, the c constant is equals to 1, and we have n squared as the g function. Okay, so this is the running time complexity for bubble sort. What does it mean exactly? It means that n squared is going to be an upper bound for the bubble sort. So essentially, this is the worst case running time. If you are familiar with bubble sort, by the way, we are going to implement it in the coming lectures, but what's crucial, that bubble sort runs in linear running time complexity, so in ordo n and not ordo n squared, if most of the items are in their sorted position. But of course, because ordo n squared is the upper bound, it is going to work just fine. It is the worst case running time for bubble sort. And essentially, it is true that bubble sort is ordo n cubed, ordo n to the power of 4, ordo n to the power of 5. You may pose the question why? Because if we assume that the g function is equals to n squared, then n cubed, n to the power of 4, n to the power of 5, these functions are larger than this green function. So what does it mean? That these function values are larger than the fn function value. So essentially, it is going to be true as well that if the running time is ordo n squared, then it is true that it is ordo n cubed, ordo n to the power of 4, ordo n to the power of 5, and so on. It is like if we say that the x value is smaller than 10, then of course it is also true that x is smaller than 100, x is smaller than 1000, and so on. Because in this case, 10 is the upper bound for the x variable. And of course, if x is smaller than 10, then it is also true that it is smaller than 100, smaller than 1000, and so on. So this is very similar with the big O notation. And what's extremely crucial, that the big O notation is going to define an upper bound bound, in this case the c constant multiplied by g of n, this is the upper bound for the running time, because this f function essentially is the running time of the algorithm. So this is exactly what we are after. We would like to have a very good guess about the running time of the algorithm for large input sizes. And of course you may pose the question that why are we interested in large input sizes? Because this is when it is crucial. Let's assume that, for example, Facebook has just 100 users. Essentially, it doesn't matter what search algorithm we use if we want to find the given user, because of course 100 item is so small that essentially if we consider every single item one by one, this is called linear search, it is going to be fast because the number of items, so the input size is so small. But what if Facebook has 2 billion users? Of course the linear search is not going to work fine because it is going to take a lot of time to consider every single item one by one. So we need a better approach. By the way, there are so-called binary search trees. So instead of considering every single item one by one, we just have to consider the base 2 logarithm of the number of items, which is going to be way faster. So this is a good example for why do we care about large input values, because of course this is when the running time of the algorithms do matter. So essentially this is the bottleneck when we are dealing with large input values. Okay, so the big ordo notation defines the upper bound for a given function, and of course the function is the running time complexity of the algorithm we are after. In the coming lectures we are going to talk about how to define the lower bound and so on. Thanks for watching. In the previous lecture we have been talking about the big ordo notation, and in this lecture we are going to talk about big omega. So first of all, what is the big omega notation? Of course, it describes the limiting behavior of a function, and of course, in this case, we are dealing with the running time complexity of an algorithm. So we are after a function that's going to describe the running time of the algorithm with respect to the input size. The input size can be the number of items we would like to sort, or the number of vertices in a graph in which we would like to calculate the shortest path, and so on. So this is the input size, and we are after the running time of the algorithm with respect to the input size. Okay, so it describes the limiting behavior of a function when the argument tends towards a particular value or infinity. It has two distinct definitions. According to number theory, it means that an fn function is not dominated by gn function asymptotically. According to complexity theory, and this is exactly what we are after, big omega means that an fn function is bounded below by a gn function asymptotically. So what does it mean exactly? The definition is going to be very similar as we have seen with big ordo notation. So we can come to the conclusion that the fn function, which is the running time complexity of a given algorithm with respect to the input size, is equals to omega, a given g function. It means that there is some c constant value where c is larger than 0 and some n0 threshold value, such that for n larger than n0, where n is the size of the input, such as the number of items we would like to sort, or the number of vertices in the underlying graph, and so on. So if n is larger than the threshold, then the absolute value of the function will be greater or equals to a c constant multiplied by the absolute value of the g function. So as you can see, when n is smaller than the threshold, sometimes the first function dominates, sometimes the other function dominates, but after n is larger than the threshold, so n is larger than n0, we can see that the fn function is larger than c times the gn function. So essentially, omega gn defines the lower bound for the fn function. So this is crucial that the big ordo defines the upper bound for the fn function, On the other hand, omega gn defines the lower bound for the fn function. So as you can see, after n is larger than the threshold, so n0, c times gn is smaller than the fn function value. And this is exactly what we are after, because we would like to define a lower bound for the running time of that given algorithm. By the way, if we assume that the algorithm has omega n squared running time complexity, then it is also true that it is omega n, omega log n, omega 1. You may pose the question why? Because if we assume that the yellow function defines n squared, so the quadratic running time complexity, which is the lower bound for our algorithm, then of course the linear running time complexity, the logarithmic running time complexity, and the constant running time complexity functions will be smaller than the yellow function, which means that they define a lower bound for the green function as well. So this is very similar that if we assume that an x variable is greater than 10, then of course it is also true that x is larger than 1, for example. Or for example, x is larger than -5. Because of course the big omega notation essentially defines a lower bound for the running time complexity of that given algorithm defined by the fn function. Okay, so that's all about the big omega notation that defines a lower bound for the running time of that given algorithm defined by fn. In the next lecture, we are going to define an upper bound as well as a lower bound for a given function. Thanks for watching. In this lecture, finally, we are going to talk about the big theta notation. So first of all, it describes the limiting behavior of a function when the argument tends towards a particular value or infinity. And of course, again, the fn function defines the running time of the algorithm with respect to the n input size. What's crucial that the fn function is bounded both below and above by a gn function asymptotically, such that fn is equals to omega gn and fn is equals to ordo gn. Of course, because big ordo has something to do with an upper bound, while on the other hand, omega has something to do with the lower bound. This is exactly what we have been talking about, that omega defines the lower bound for the fn function, while on the other hand, the big O notation defines the upper bound for the fn function. So we can come to the conclusion that fn is equals to theta gn, which means that we can find c1 and c2 constant values, these are larger than 0, and some n0 threshold, such that for n larger than n0, the fn function value that represents the running time of the algorithm is smaller or equals than c1 multiplied by the gn function, and it is larger than c2 multiplied by the gn function, and we are dealing with the absolute value of these functions, which means that the upper bound of the fn function is c1 multiplied by gn, and the lower bound for the fn function is c2 multiplied by the gn function. So essentially, big theta defines the lower as well as the upper bounds for the fn function. In the next lectures, we are going to talk about concrete examples, and we make sure to understand these notations exactly. Thanks for watching.
Hi, in this video we are going to talk about concrete examples for analyzing running time complexities, and here we are going to focus on the three notations. So let's suppose that we have a function fn is equal to 3 times n squared minus 100 times n plus 6. Let's prove that the fn is equal to ordo n squared. So, the definition for the big ordo is that the absolute value of fn is smaller or equal to the c times the absolute value of gn. So if n is large enough, then we can get rid of the absolute values. So we have to make sure that the 3 times n squared is greater or equal than 100n. And basically we just have to solve this equation. So whenever the n is greater than 34, then we can get rid of the absolute values. So in this case, the fn absolute value is equal to the fn itself. Why? Because from now on we are going to deal with positive values, and the absolute values of positive values is going to be the same as the original values. So in this case, 3 times n squared minus 100 times n plus 6 is smaller or equal to the c times n squared according to the definition. So we can come to the conclusion that if the c is equal to 3 and the n0 threshold is equal to 34, that is going to be okay, this big ordo notation. So the fn is equal to the ordo n squared, because 3 times n squared minus 100n plus 6 is going to be smaller or equal to 3n squared when the n is greater than 34. It is true because the difference is 100n plus 6. So that's why we have proved that the fn is equal to the ordo n squared. What does it mean? That whenever the n is greater than 34, then we are sure that the 3 times n squared is going to be above the 3 times n squared minus 100 times n plus 6 function. So this c times gn is going to be greater than equal to the fn, and basically that's the definition for the big ordo notation. Let's prove that the fn is equal to the ordo n cube. The definition is that the fn absolute value is smaller or equal to the c times gn. If the n is large, then we can get rid of the absolute values as in the previous example. So we have to make sure that this 3 times n squared is greater or equal to 100n. So the n has to be greater than 34. So the n0 threshold value is equal to 34, and we can get rid of the absolute values because we are sure that the fn values are positive values, and the absolute values of the positive values are the original values itself. So the 3 times n squared minus 100n plus 6 is smaller than 3 times n squared, which is smaller than the n cube. Because for 3 times n squared we have seen that the fn is equal to the ordo n squared. That's why it's sure that it is ordo n cube as well. So for example, if the c is equal to 1 and the n0 is equal to the 34, then it's going to be true that the fn is equal to the ordo n cube. And basically, it is true in the main that if the fn function is big ordo n to the power of k, then the fn is equal to ordo n to the power of k plus I, where the I is greater than 1. It is also true. In the previous example, we have seen that if the fn is equal to ordo n squared, then it is also true that it is equal to ordo n cubed. So if it is ordo n to the power of k, then it is also true that ordo n to the power of k plus I is going to be satisfied. And why? Because the big ordo is an upper bound for a given fn function. So if the n to the power of k is an upper bound, of course the n to the power of k plus I will be an upper bound. Simple math. So for example, the bubble sort has ordo n squared running time complexity. Then it's also going to be true that the bubble sort is in ordo n cube, or ordo n to the power of 4, or ordo n to the power of 5, or n to the power of 1000. It's going to be true as well, because this is how big ordo notation works. Let's prove that the fn is not equal to the ordo n. We have to find the n values in order to get rid of the absolute values. So if the n0, the threshold, is equal to 34, then we can get rid of the absolute values. And the fn must be smaller or equal to the c times n. And basically, we are not able to solve this equation, c times n to the power of 2 minus 100n plus 6 is smaller than equal to the c times n. We have already come to the conclusion that 3 times n squared minus 100n plus 6 is greater than equal to the n squared if the n0 is equal to 34. So basically, we are not able to solve this equation that the c times n is greater or equal to the n squared. So that's why we can come to the conclusion that the fn is not equal to ordo n. So basically, the linear function is not above this 3n squared minus 100n plus 6 function. And basically it is true. Let's prove in the end that the fn is equal to the omega n squared. So the fn absolute value is greater or equal to the c times absolute value of gn. This is the concrete mathematical definition for the big omega notation. We have to calculate the threshold value. It's going to be the n0 as we have seen in the previous examples, so we can get rid of the absolute values. And we have to solve the equation that the fn is greater or equal to the c times n squared. So 3 times n squared minus 100n plus 6 is greater than the c times n squared. So we can choose the constant, the c constant, to be equal to 1. And we have to solve this equation. And basically when the c is equal to 1 and the n0 is equal to 34 as we have calculated, then it's going to be a lower bound, which is the omega notation itself. So it is true that the fn is equal to the big omega n squared. Okay. And what does it mean? It means that we have calculated that this fn equal to 3n squared minus 100n plus 6 is equal to ordo n squared. And we have calculated in the previous slides that it is equal to omega n squared. And that's why we can tell that fn is equal to the theta n squared. And usually it is a quite common mistake, by the way. It's not that important, but usually we use big omega whenever we should use the big theta notation. So the difference is that for the theta, we know that it's going to be in a range. For the ordo, we just define the upper bound. We know nothing about the lower bound. Basically, if we say that an algorithm is ordo n squared, it means that it can be faster. It can have logarithmic time complexity. It can have constant time complexity. If we say that it is theta n squared, we say that it's not going to be faster than n squared, and it's not going to be slower than n squared. It's going to be in the range. But for the ordo, we just define an upper bound. I'm not sure whether it is clear for you, and basically this is not that very important in order to understand data structures and algorithms in the main, but basically to be able to get a very good grasp of algorithms, I think that these notations are worth to be understood. Thanks for watching.
In the previous lectures, we have been talking about the fundamental basics of running time analysis with the help of big ordo, big omega, and big theta. In this lecture, we are going to talk about algorithms running times. So first of all, this is what we have been talking about in the previous lectures, that we are after the relationship between the running time of a given algorithm with respect to the input size. So the input size is the number of items we are dealing with. For example, the number of items we would like to sort. For example, the number of vertices in a graph in which we would like to calculate the shortest path and so on. So we have the fn function, which is the running time, and we have the size of the input. So first of all, let's talk about the factorial running time complexity. This is ordo n factorial. What does it mean? That the algorithm that has factorial running time complexity scales with the factorial function. Of course, these algorithms are extremely slow because there is a huge amount of possible configurations, so essentially the search space is enormous. So these are extremely slow algorithms. Then we have the exponential running time complexity, where c is a constant. So for example, 2 to the power of n, 3 to the power of n, 4 to the power of n, these are the exponential running time complexities. Of course, exponential running time complexity is still quite slow. So we can come to the conclusion that algorithms with factorial running time complexity or exponential running time complexity have no practical applications because these algorithms are extremely slow. Then we have the polynomial complexity, where k is larger than 1, such as n squared, n cubed, n to the power of 4. These are the polynomial running time complexity algorithms. These are considered to be slow as well. So the first running time complexity that is working fine is the so-called linear-arithmic running time complexity, ordo n multiplied by the logarithm of n. So this is a typical running time complexity, for example, when we are dealing with sorting algorithms, and it is working fine. Then we can do better with linear running time complexities, such as, for example, if we want to find the maximum item or the minimum item in a one-dimensional array and so on. Then we can do even better with logarithmic running time complexity, ordo logN. So the running time of the algorithm scales with the logarithmic function, so it is quite fast. And of course, the best running time complexity we can achieve is the constant running time complexity. What does it mean? It means that the running time of the algorithm is essentially independent of the input size. So for example, if we want to swap two items in an underlying one-dimensional array, of course it is independent of the size of the underlying one-dimensional array. No matter we are dealing with 10 items or 10 billion items, the running time is going to be the same. Okay, so constant running time complexity is the fastest running time possible, and essentially, if you are familiar with algorithms and data structures, the aim of these algorithms is to reduce the running time complexity to constant running time complexity. So for example, if we have an unsorted one-dimensional array of integers and we want to find a given item, then we have no other option but to consider every single item one by one. Essentially, we end up with linear running time complexity. By the way, don't worry, we are going to consider examples for every single running time complexity, and it is going to be clear. What's crucial that we can reduce the running time if we have a sorted data structure. For example, a sorted one-dimensional array. If we are looking for an item in a sorted array, this is called binary search, then we can end up with logarithmic running time complexity. And if we use hash functions and hashing, such as with hash maps and dictionaries in Python, then we can achieve ordo 1 constant running time complexity. So as you can see, we can reduce linear running time complexity to even constant running time complexity if we have a good data structure. So this is why data structures are extremely powerful, because we can reduce the running time significantly. Okay, so these are the running time complexity classes. What's crucial that factorial complexity, exponential complexity, and polynomial complexity related approaches have no practical applications because these are considered to be slow approaches. We like linear arithmetic complexity, linear complexity, logarithmic complexity, and constant running time complexity. These are the complexity classes with practical applications because these are considered to be quite fast. So let's take a look at a concrete example for the constant running time complexity. Ordo 1 running time means that the running time of the given algorithm is independent from the n input size. For example, if we want to swap two integers with known indices in an underlying one-dimensional array, or we want to decide whether an integer is even or not, so these are extremely fast operations and these are independent from the input size. So it doesn't matter whether the underlying one-dimensional array contains 1 billion items or just 10 items. If we know the indices of two items, then we can swap them in ordo 1 constant running time complexity. What about logarithmic running time complexity? It means that the running time of the given algorithm scales with the logarithmic function, such as finding an arbitrary item in a sorted array with binary search, or for example, we can check whether is there a cycle in an underlying directed graph or not. It is extremely crucial in Kruskal's algorithm, so this is called the disjoint dataset, and of course it is working quite fine. Then we have the linear running time complexity. Ordo n running time means that the running time of the given algorithm scales linearly with the input. So essentially, if we double the input size, then the running time will be doubled as well. So it scales linearly, such as finding the maximum item in an underlying one-dimensional array. In this case, as you can see, 20 is the maximum item, so we have to consider every single item exactly once. This is why it has linear running time complexity. Or by the way, we have Cadane's algorithm for finding the maximum subarray, which is extremely crucial in computer vision. So this is the linear running time complexity. What about the linear arithmetic running time complexity? This linear arithmetic running time complexity is quite close to linear running time complexity. So essentially, we can come to the conclusion that algorithms with ordo n logN is quite fine. These are fast algorithms, such as, for example, quicksort or merge sort, or when we want to find the closest pair of points with divide and conquer algorithms. So this is the linear arithmetic running time complexity. Then we have the polynomial running time complexity n to the power of k when k is larger than 1, such as the quadratic running time complexity n squared, we have n cubed, and so on. Ordo n squared, for example, is called quadratic running time complexity when the running time scales quadratically with the input. What does it mean? If we double the input size, then we end up with 4 times the running time. So this is the quadratic running time complexity. For example, sorting algorithms like insertion sort or selection sort, or for example, the brute force matrix multiplication has ordo n cubed running time complexity. By the way, we don't like polynomial running time complexity related approaches. Insertion sort is working fine when we are dealing with just a few items. So for example, insertion sort can be used as a subroutine when the underlying array contains just a few items. Okay, so sometimes we can use these polynomial running time complexity related approaches, but usually these are considered to be slow algorithms. And of course we have the exponential running time, which is extremely slow. So we have ordo c to the power of n. It means that the running time of the given algorithm scales exponentially with the input. So for example, the Towers of Hanoi problem with recursion has ordo 2 to the power of n running time complexity, or calculating the Fibonacci numbers takes ordo 2 to the power of n as well. So as you can see, in this case, the running time scales exponentially with the input size. If we double the input size, then essentially the running time will be exponentially slower. Okay, this is the exponential running time complexity. And finally, we have the slowest approach possible with factorial running time complexity. It means that the running time of the given algorithm scales with the factorial function, such as solving the traveling salesman problem, which is essentially the same as finding the Hamiltonian cycle with the smallest total sum of edge weights. And of course, it has ordo n factorial running time complexity because there are n factorial possible combinations. So for example, this is a valid Hamiltonian cycle. This is another Hamiltonian cycle, this is another Hamiltonian cycle, and we are looking for the Hamiltonian cycle where the sum of the edge weights is as low as possible. So essentially it is a minimization problem. And of course, as you may guess, that this factorial running time complexity is extremely slow. But of course, this problem is essential in logistics, for example. So you may pose the question that how to deal with factorial running time complexity and exponential running time complexity related problems. And the solution is that we have to use some kind of heuristics or meta-heuristics. For example, we can solve this traveling salesman problem quite fast with the help of genetic algorithms or simulated annealing. By the way, if you are interested in algorithms, data structures, heuristics and meta-heuristics and artificial intelligence in the main, then check out my other courses on these topics. Thanks for watching. In the previous lectures, we have been talking about running time analysis of given algorithms. We have been talking about the big ordo notation, and in this lecture we are going to talk about complexity classes. So first of all, let's talk about the most crucial complexity classes, and then we are going to consider them on a one-by-one basis. So if we assume that we have the complexity on a one-dimensional measure, then we can come to the conclusion that the first complexity class is polynomial. These are the algorithms with real-world applications, such as as merge sort, quick sort, minimum and maximum finding in binary search trees, or for example finding the shortest path with the help of Dijkstra's algorithm, finding the minimum spanning tree with Kruskal's algorithm. So these are the algorithms with polynomial running time. Essentially, this is what we have been talking about in one of the previous lectures, that polynomial running time complexity, linear-arithmic running time complexity, linear running time, logarithmic running time, and constant running time, these are the running times we like. The exponential running time complexity and factorial running time complexity is so slow that there are no practical applications of these kinds of algorithms. So we have the polynomial class, then we have the so-called non-deterministic polynomial, this is called NP. These are the exponential or factorial running time complexity algorithms, such as for example finding the Hamiltonian cycle in a graph, or for example solving the towers of Hanoi, solving the knapsack problem, and so on. So it is extremely hard to find the solution for these kinds of problems, but if we have the solution, we can verify that solution quite fast in polynomial time. These are called non-deterministic algorithms. Then we have NP complete problems. These are the hardest non-deterministic polynomial problems. And then we have the hardest possible problems. These are called NP hard problems. So what does it mean exactly? If we have the polynomial class, then we can define the non-deterministic polynomial class, and we will talk about that the polynomial complexity class is within the non-deterministic polynomial class. Then we have the extremely hard problems. These are the NP hard problems. And then we have the so-called NP complete problems that are the hardest problems in the non-deterministic polynomial complexity class. First of all, let's talk a bit about the polynomial complexity class. P stands for polynomial, of course. All the decision problems that can be solved with deterministic Turing machines using polynomial amount of computational time. This is exactly what we have been talking about, that essentially ordo n to the power of k, ordo n log n, ordo n, ordo log n, ordo 1, these are the running time complexities that belong to the polynomial class, which means that we can solve these problems using polynomial amount of computational time. What's crucial that these problems are efficiently solvable, but not all of these problems have practical applications, such as with bubble sort. Bubble sort is working fine, it has polynomial running time complexity, it is within the P complexity class, but of course it has no practical applications because merge sort, quick sort, and heap sort are working better. These are faster sorting approaches. So despite the fact that a given algorithm may belong to the polynomial complexity class, it may happen that it doesn't have any practical application. Okay, so that's all about the polynomial complexity class. By the way, most of the algorithms that we use in modern applications belong to the polynomial complexity class. For example, if we design an algorithm for finding a given user in Facebook or Instagram, of course these algorithms belong to polynomial complexity class. If we want to find the shortest path on Google Maps, of course this algorithm belongs to the polynomial complexity class. What about the non-deterministic polynomial class? NP stands for non-deterministic polynomial. These problems are exponentially hard to solve, but if we have the solution for the problem, then we can verify this solution in polynomial time. This is what we have been talking about, that P is a subset of NP. Why? Because of course we can verify whether the polynomial problem is working fine or not in polynomial running time. Of course, because essentially we can solve the problem itself in polynomial running time. So for example, if you have a one-dimensional array of integers and I tell you that the maximum item is 20, then what do you have to do in order to verify whether it is true or not? Essentially, you just have to consider every single item one by one, and then you can verify whether 20 is the maximum item or not. So essentially, you are going to solve the problem because it can be done in polynomial running time complexity. So this is why P is a subset of NP. Non-deterministic polynomial algorithms are extremely slow. They have exponential or factorial running time complexity. But if we have the solution, we can verify it in polynomial time. Of course, it is true for P as well. If we have the solution for a given polynomial complexity class related problem, then we can verify it in polynomial time, of course. By the way, one of the most important problems is whether P is equals to NP or not. It is quite a confusing question because most of the problems that have belonged to non-deterministic polynomial now belong to polynomial. For example, finding large prime numbers. It has been a non-deterministic polynomial approach in the sense that it is exponentially hard to find large prime numbers with the brute force approach. But there is a fast algorithm that can solve this problem in polynomial running time. So what does it mean? The problem that has belonged to NP now belongs to P complexity class. So this is why maybe every single problem that belonged to non-deterministic polynomial, in the future they will belong to polynomial because computer scientists will find a way to solve these problems more efficiently. So this is an important problem whether P is equals to NP or not. Let's take a look at concrete examples for NP. For example, integer factorization. If we want to calculate the prime factors or the integer factors of a given large integer, it is an exponentially hard problem to solve. So it is very hard to solve the problem, but if we have the solution x and y, for example, then we can verify it by multiplying the two numbers x multiplied by y, which is of course a fast operation. So this is what we have been talking about a few minutes earlier, that this is the definition for NP problems, that finding the solution for the problem is extremely hard, but if we have a solution, then it is extremely fast to verify it. So this is exactly what's happening here, and by the way, this is the fundamental operation in cryptography. This is why we multiply two large prime numbers in the RSA crypto system, because it is exponentially hard to find the prime numbers for a large integer. Another example is the knapsack problem. So given a set of items, each with a weight and a value, determine the number of each item to include in a collection such that the total weight is less than or equal to a given limit and the total value is as large as possible. This is the knapsack problem. It has exponential running time complexity because for every single item we have to decide whether to include in the collection or not to include in the collection. And of course, if we have n items, then the running time complexity is ordo 2 to the power of n, which means that it has exponential running time complexity. It is extremely hard to solve this problem, but if we have the solution, then we can verify whether it is a valid solution or not in polynomial running time complexity. Okay, what about the NP complete class? These are the hardest problems in NP. So this is what we have been talking about a few minutes earlier, that NP complete problems are the hardest problems in NP. And by the way, we can transform an NP complete problem into an NP problem in polynomial time. This is called Karp reduction. It is important in computer science because if we manage to find a polynomial algorithm for an NP complete problem, then of course it means that P is equals to NP. Why? Because NP complete problems are the hardest problems in NP. So if we can solve an NP complete problem, it means that we can solve any NP problems as well, which means that P is equals to NP. So this is why it is an important complexity class. And by the way, again, if we know the solution for an NP complete problem, then it is easy to verify it in polynomial time. So again, the basic concept is that it is extremely hard to find the solution for these kinds of problems, but if we have the solution, then it is easy to verify it in polynomial time. By the way, the time required to solve these problems using any currently known algorithm increases very quickly as the size of the problem grows. This is exactly what we have been talking about, that the factorial running time complexity related algorithms, the exponential running time complexity related approaches belong to the NP complete and NP hard complexity classes. The polynomial complexity, linear arithmetic complexity, linear running time complexity, logarithmic running time complexity, these belong to the P class, so to the polynomial class. Let's take a look at a concrete example for the NP complete problems. A typical example is graph coloring. So the problem is that we have to color the vertices of a G graph with V vertices and E number of edges, such that no two adjacent vertices share the same color. By the way, if we have C number of colors and we have N vertices, then as you can see, it has exponential running time complexity, ortho C to the power of N. And of course, the solution can be found with backtracking algorithm and with the help of recursion. I have another course on dynamic programming and recursion and backtracking related algorithms. So if you are interested in coloring problem, check out my other courses. So as you can see, this is a valid solution because no two adjacent vertices share the same color. And as you can see, we need 4 colors in order to solve this problem. So this is a typical NP complete problem. Then we have NP hard problem, problems that are at least as hard as the problems in NP class. By the way, we can transform an NP hard problem into an NP complete problem in polynomial time with the help of carp reduction. So this is what we have been talking about, that we have the NP class. The hardest problems in NP is called NP complete problems, and NP hard problems are the problems that are at least as hard as NP complete or harder. So these are the hardest problems in computer science. Such as, for example, the halting problem. Given a software and the input, a good question is whether it will run forever or not. This is a decision problem with yes or no possible answers, and of course it is NP hard. It is extremely hard to decide whether a given application is going to run forever or not. Or another example is the traveling salesman problem, when we have to find the minimum Hamiltonian cycle. And because there are n factorial possible combinations, if we have n vertices in the underlying graph, of course it has factorial running time complexity, which means that it is extremely hard to find the solution. But if we have the solution, then we can verify whether it satisfies the conditions or not in polynomial time. So again, as you can see, for NP hard problems, it is true as well that it is extremely hard to solve the problem, but if we have a solution, then it is easy to verify whether it is a good solution or not. That's all about complexity classes. Thanks for watching. In this lecture, we are going to talk about how to deal with for loops, because most of the times the algorithm running time can be approximated by the number of nested for loops. First of all, let's consider the constant running time complexity. Constant running time complexity means that the running time of the given algorithm is independent from the input size. So no matter we are dealing with 10 items or 10 billion items, the running time of the algorithm will be the same. For example, when we swap two integers, and of course we know the indices of those given integers in a one-dimensional array, or for example, if we multiply two integers, or we want to decide whether an integer is even or not. So for example, when we swap two integers in an underlying one-dimensional array, this is the nums variable, essentially we just have to do something like this, and these operations have ortho 1 constant running time complexity. This is why the swap operation itself has ortho 1 constant running time complexity. It is independent of the input size. So no matter that how many items we are dealing with, the running time of this operation will be the same. This is called constant running time complexity. By the way, we are going to implement a given example associated with every single running time complexity. So this is going to be clear in the coming lectures. What about linear running time complexity? Linear running time complexity means that the running time of the algorithm scales linearly with the input. So if we double the size of the input, then the running time will be doubled as well. And usually it means a for loop when the inner operation takes order 1 running time complexity. For example, when we sum up the values in a one-dimensional array, or when we want to find the given item in a one-dimensional array, this is called linear search. For example, we are looking for the maximum or we are looking for the minimum. These operations have order n linear running time complexity. And as you can see, linear running time complexity usually means that we have a single for loop. We consider all the items starting with the first one up to the last one. And it is absolutely crucial that this for loop depends on the n input size. Okay, and of course the inner operation has order 1 constant running time complexity. For example, we check whether that given item with index I is the item we are looking for or not. So this is the so-called linear search. Or for example, when we sum up the values, what do we have to do? We just have to sum up the given values. That can be done in order 1 constant running time complexity. So if we have a single for loop that considers every single item of the underlying data structure and the operation has order 1 running time complexity, this is when we end up with order n linear running time complexity. What about quadratic running time complexity? Quadratic running time complexity means that the running time scales quadratically with the input. So if we double the input size, then we end up with 4 times the original running time. If we multiply the input size by 10, then the running time will be multiplied by 100. And usually it means a nested for loop. So as you can see, in this case we have 2 for loops, for I starting with 0 up to n, and we have a nested for loop j starting with 0 up to n, and the inner operation takes order 1 constant running time complexity. Because we have 2 nested for loops, this is why we end up with quadratic running time complexity. For example, summing up the values in a 2-dimensional array, finding a given item in a 2-dimensional array, essentially we have to consider every single row and every single column of the 2-dimensional data structure. So this is why we end up with quadratic, so order n squared running time complexity. What if we have, for example, something like this? We have a for loop, I starts with 0 up to the last item, but the inner for loop starts with 0 up to just I, which is the index of the outer for loop. You may come to the conclusion that this is not going to be a quadratic running time algorithm because we are not going to consider as many items as in the previous example. So here, as you can see, we consider every single item with both of the for loops. In this case, we consider just fewer items, but we can come to the conclusion that it is still order n squared, because order n squared divided by 2 is essentially order n squared. So when we are dealing with asymptotic analysis, we don't care about constants such as 0.5. It is essentially the same. It has quadratic running time complexity. What about order n cubed? In this case, we have 3 nested for loops. We have the I that starts with 0 up to n, we have j that starts with 0 up to n, we have k that starts with 0 up to n, and then we do some constant running time complexity related operation. For example, with matrix-matrix multiplication. The brute force approach has order n cubed running time complexity. By the way, this is a tricky question, that what is the running time of this algorithm when we have 3 nested for loops, but the nested for loops consider a constant amount of items. It is extremely crucial that if we have a for loop that's going to consider just a constant number of items, essentially it has constant running time complexity. Why? Because these operations, so the second for loop and the third for loop, are not going to scale with the input size, because no matter that how many items we have in our data structure, we are going to make 10 iterations with the second for loop, and we are going to make 20 iterations with the third for loop, which means that it is a constant number of iterations. So because the first for loop considers all the items starting with 0 up to the input size. This is why this algorithm has ortho and linear running time complexity, despite the fact that we have 3 nested for loops. So we can come to the conclusion that we have nested for loops, but the number of operations are independent of the n input size for the second for loop and for the third for loop. So they do a constant number of operations that is independent of the n input size. So we can come to the conclusion that there is just a single for loop that scales with the n input size. So this is why we end up with linear running time. So it is absolutely crucial that the number of nested for loops are not necessarily polynomial running time complexity. We have to consider the for loops exclusively that scales with the n input size. Okay, and by the way, the number of nested for loops that scales with the n input size defines the running time of the algorithm. So if we have nested k for loops, when every single for loop scales with the n input size, then it means polynomial running time complexity, ortho n to the power of k. So if we have just a single for loop, k is equals to 1, then we end up with linear running time complexity. If we have k is equals to 2, then we have quadratic running time complexity. If we have, for example, 6 nested for loops, when every single for loop scales with the n input size, then we have ortho n to the power of 6 as the running time. Okay, so that's all about for loops and running time analysis. By the way, we are going to take a look at several examples, and it is going to be clear in the coming lectures. Thanks for watching. In this lecture, we are going to talk about the logarithmic running time complexity, and we are going to focus on binary search or logarithmic search. So binary search or logarithmic search is a method for finding the position of an item in a sorted list. So it is extremely important that binary search can be used only if the underlying data structure is sorted. The algorithm makes logarithm and comparisons in worst case. Hence, the running time complexity is logarithmic, ordo logN. And of course, it has practical and real-world applications, as ordo logN running time complexity is quite favorable. It is very close to ordo 1 constant running time complexity. So this is why we like binary search, and basically this is the intuition behind binary search trees, that we would like to use binary search on the items stored in the data structure. Anyways, we are not going to talk about binary search tree, we are going to focus on binary search. So for example, we have a one-dimensional array or a list data structure with items -4, -1, 0, 1, 2, 9, 14 up to 60. What's crucial that, as you can see, this data structure is sorted, and because it is a sorted data structure, we can use binary search. So what is the binary search algorithm? The binary search algorithm is going to take a look at the middle item. Of course, in this case, there's no middle item because we have an odd number of items in the data structure. So we have two middle items basically. We are going to use the left out of the two middle items. So what's crucial that we pick the middle item, or approximately the middle item, and we compare it with the item we are looking for. For example, we are looking for the item with value 1. Of course, 1 is smaller than 9, and we know for certain that it is a sorted data structure. So what does it mean? That we can discard half of the data structure in every single iteration, because we have checked item with value 9. The item we are looking for is smaller than 9, so we know for certain that the item we are looking for is in the left subarray. So in every iteration we can discard half of the array, and this is why the final running time complexity will be ordo logN, which means that the algorithm makes logarithm and comparisons in worst case. Then again, what do we have to do? We have to choose the middle item. 0 is smaller than 1, so in this case we can discard the left half of the array. And we have just two items, so again we pick the middle one, and this is the item we are looking for. So we have to make 3 iterations in order to find number 1 with the help of binary search. So it is extremely crucial that in this case we choose the middle item because the underlying data structure is sorted, which means that in every iteration we can discard half of the items of the actual array. And this is why the algorithm makes logarithm and comparisons in worst case. You may pose the question that what does it mean worst case? In this case, worst case scenario is when we consider the item we are looking for in the last iteration. So we have already considered several items, and finally we have just an array with a single item, basically the item we are looking for. So this is why it is extremely powerful, because we just have to make logN comparisons in worst case. So let's take a look at the implementation, and it is going to be clear. We have a public static. We will return with an index of the given item we are looking for, and we have the search method. Of course, we have the one-dimensional array of integer. These are the numbers, and of course we are looking for a given item. First of all, we have to define the leftmost item and the rightmost item. Left is equals to 0, and we have integer right, which is equals to nums.length -1, because indices starts with 0. So for example, if we have something like this, then left is going to represent the leftmost item with index 0, right will represent the rightmost item with nums.length, so the number of items 1, 2, 3, 4, 5, but of course indices starts with 0 in Java, so this is why we have to decrement it by 1. So in this case we have index 4 that is pointing to the rightmost item. And of course we have to iterate, so while left is smaller or equals than the right index, what do we have to do? First of all, we have to generate a middle index, which is equals to left plus right, and we have to divide it by 2. So this is how we generate the index for the middle item. Of course, we have to check whether we have found the given item or not. So if nums at the middle index is equals to the item we are looking for, then we return with the middle. Otherwise, we have to discard the left half or the right half of the array. So what do we have to check? If nums at the middle is smaller than the item we are looking for, then we know for certain that the item is in the right side of the array, because this one-dimensional array is sorted. This is what we have been talking about, that the array is sorted. This is when we can use binary search. So in this case, if the item is larger than the middle item, then we know for certain that we can discard the left half of the array, which means that the left index is updated to be the middle plus 1. And of course, else we have to discard the right half of the array. So we have the right, which is equals to middle minus 1. And of course, after the while loop, it may happen that this is a search miss, so we return with minus 1. So this is the search miss when the item is not present in the one-dimensional array. So what does it mean exactly? If we have, for example, a one-dimensional array 1, then 2, 3, 4, 5, 6, 7, 8, and 9, for example, and we are looking for 9, what do we have to do? We have to generate the middle item, and because we know that the item we are looking for is larger than the middle item, we discard the left half of the array, and we know for certain that we just have to consider the right side of the array, so the left index will be equals to the middle index plus 1, and then in the next iteration we just have to consider these 4 items. So as you can see, in every single iteration we can discard half of the array. And by the way, you may pose the question that why it has ordo logN logarithmic running time complexity. So how many times we can divide n items to end up with 1. And of course, we have to calculate that 1 is equals to the number of items divided by 2 to the power of x, where x is the number of times we can divide n items in order to end up with 1. So if we solve this equation, then we get x then logarithm 2, which is equals to 1, by the way, but anyways, and we end up with log n, which means that x is equals to log n. So we can come to the conclusion that we can divide n items log n times in order to end up with 1, which means that in a worst case scenario, we have to make log n operations. So this is why it is an extremely fast approach. So I am going to copy and paste the code from bubble sort, for example. So let's create a one-dimensional array of integers, for example, with 1 million items. And of course, we have to make sure that it is sorted. So we are going to start with 0, and I is less than nums.length. And of course, in every single iteration, we increment I by 1. Sorry for that, we have the numbers. So this is how we create a one-dimensional array with 0, 1, 2, 3, 4, 5, and so on. So of course, these items are sorted by default. And then we can search for the last item, for example. So we have the numbers and we have the last item, which is equals to the numbers.length minus 1, because indices starts with 0. So if we save and rerun the application, then it is going to be extremely fast. Let's define the start, which is equals to the system.current time in millis. And after the search operation, let's print out. So we have println time taken, sorry for that, time taken, and we have the system current time in millis minus start. Okay, so if we have something like this, we save and rerun the application, then as you can see, binary search is so fast that essentially it takes 0 milliseconds to finish with the computation. So maybe I am not able to generate as many items such that the running time is greater than 0 because it is extremely fast. Of course, logarithmic running time complexity is very close to ordo 1, which means that it is faster than linear running time complexity, and linear running time complexity is fast as well. Okay, so we are not able to measure the running time of binary search because it is so fast that essentially it takes 0 milliseconds to finish with the computation. Thanks for watching. In this lecture, we are going to talk about linear running time complexity related approaches focusing on linear search. So first of all, what is the problem itself? Let's assume that we have a one-dimensional array of unsorted items. Just for demonstration purposes, we are going to use integers, and we want to find a given item. It is crucial that the underlying data structure is unsorted, because if we have a sorted one-dimensional array, then we can use binary search, we are going to talk about it later, and we can end up with logarithmic running time complexity. So this is crucial that the underlying array is unsorted. If we know the index of the item we are looking for, of course we can get it in ordo 1 constant running time complexity. This is the main feature of arrays, that if we know the index of a given item, then we can get it extremely fast. Usually, of course, we don't know the index of the item we are looking for, so we have no other option but to consider every single item one by one. So this is why we end up with a linear running time complexity algorithm. So let's take a look at a concrete example. We have a one-dimensional array of integers 12, 4, -2, 1, 20, 0, 8, and 3. And for example, we are looking for the integer 12. Because this is the first item, we are going to find it in the first iteration. This is called best case scenario. This is when we are looking for an item that turns out to be the first item of the data structure. And because this is the first item, essentially we can get it in ordo 1 constant running time complexity. So what is the best case running time of linear search? It is ordo 1 constant running time. What if we are looking for an item that is approximately in the middle of the data structure? For example, we are looking for integer 1. Of course, we have to consider every single item until we find the item we are looking for. This is called the average case scenario because we consider half of the data structure. So in this case, we are looking for an item that turns out to be in the middle of the data structure. What is the running time complexity? We have to consider n divided by 2 items, so the running time is ordo n divided by 2, but of course in asymptotic analysis we don't care about constants, so ordo n divided by 2 is equals to ordo n linear running time complexity. What if we are looking for an item that is at the end of the data structure, so we are looking for integer 3, we have no other option but to consider every single item one by one until we hit integer 3. This is the item we are looking for, and by the way, this is the so-called worst case scenario because we have to consider every single item of the data structure until we find the item we are looking for as the last item of the data structure. What is the running time complexity? Of course, we have to consider every single item one by one, so it has linear running time complexity. By the way, usually when we are dealing with running time analysis, we are after the worst case scenario because of course this is the bottleneck of the algorithm. We don't care about the best case scenario because usually this is not going to happen. We are after the worst case scenario. So let's take a look at the implementation. Let's take a look at a concrete example. For example, we have a public static integer. This is going to return with the index of the given item we are looking for. And for example, we have the search. Of course, we have the one-dimensional array, the data structure itself, we have the numbers, and of course we have the item we are looking for. So what do we have to do? Essentially, we have to consider all the items, so integer I, or we can say that this is the index, it is equals to 0. The index is smaller than the the length of the one-dimensional array, and of course in every single iteration we keep incrementing the index by 1. And what do we have to check? If the nums at the given index is equals to the item we are looking for, then we are going to return with the index itself. And if we have considered every single item exactly once without any success, then we return with -1. So this is the search miss. And otherwise we consider all the items one by one. So this is why it has ortho and linear running time complexity. As you can see, this for loop scales with the number of items in the one-dimensional array. So essentially the input size is the number of items. This is the capital N. And of course we have a single for loop. What is the running time complexity of this approach? Of course it has ortho 1 constant running time complexity, because essentially we keep comparing two integers. It is extremely fast. So this is what we have been talking about, that if we have a for loop from 0 up to the input size, which is the size of the underlying one-dimensional array in this case, and in every single iteration we do an operation that has ortho 1 constant running time complexity, this is when the final running time complexity is linear running time complexity. So this is why this method has ortho and linear running time complexity, which means that if we double the input size, so we have 2 times n, then the running time will be doubled as well. Okay, so this is the so-called linear search. Let's take a look at a concrete example. We have numbers. For example, we have 1, 2, 3, 4, 5, 6, 7, and 8. And of course we can print out, so system out and println. We just have to call the search method with the numbers. And for example, we are looking for the integer 3. What is going to be the result? We have index 0, index 1, index 2. So the result should be 2. So we are able to find the index of the given item in linear running time complexity. If we are looking for an item that is not present in the underlying data structure, then we get -1. Okay, let's implement a method that's going to sum up the values in the array. So what do we have to do? We have a public static, the integer is going to be the result, and of course we have a one-dimensional array of numbers. And what do we have to do? We have to define a variable sum is equals to 0. We have to consider integer I is 0, I is less than the nums.length, and of course in every iteration we increment the value by 1. And what do we have to do? Sum plus equals to the numbers one-dimensional array at the given index. And finally we return with the sum itself. So essentially this is the bottleneck of the algorithm, and of course because we have a simple for loop that scales with the input size, and within the for loop we do an operation that takes ortho 1 constant running time because we just sum up the values. So essentially in every single iteration we have to sum up two integers, which is extremely fast. This is why again we end up with a linear running time complexity algorithm, which means that if we double the input size, then the running time scales linearly, so it is going to be doubled. Let's take a look at a concrete example. We have a one-dimensional array, for example, with 1,000 items. So if we have something like this, then we have 4 integer I is equals to 0, then we have I less than the numbers.length, and of course in every single iteration we increment I by 1. And just for demonstration purposes, we are going to use the index as the actual value in the one-dimensional array. So what does it mean? We will have 0, 1, 2, 3, 4, 5, and so on. And of course, we are going to sum up these values. So if we have, for example, 100,000 integers, and we would like to sum up these values, so we call the sum method. Of course, it is going to work fine, but we would like to measure the running time. So we can use long the start, which is equals to system current time in millis. This is how we can get the actual time in milliseconds. And then we calculate the sum. We are not going to print out the value. We just calculate the sum itself. And then we print out system out and println that time taken, and we print out the actual time, which is system.currentTime in millis minus the start. This is how we calculate the time needed to sum up all the values in the underlying one-dimensional array. And of course, sorry for that, we have system.out.println. So for example, if we sum up 10 million items, then what's going to be the running time? As you can see, it takes 5 milliseconds for Java to sum up 10 million integers. What if we multiply the number of items by 10? Then of course, because we are dealing with a linear running time related algorithm, we expect that the running time will be multiplied by 10 as well. So we expect something around 50. It is working fine. It is not going to be 100% accurate, but as you can see, the running time is approximately 10 times slower. What if we have even more integers? I guess we have 1 billion items. Then of course, because we have linear running time complexity, if we multiply the number of items by 10, then we expect that the running time will be multiplied by 10 as well. This is called linear scaling. So if we save and rerun the application, then as you can see, it takes 300 milliseconds. We have multiplied the number of items by 10, and the running time has been multiplied by approximately 10 as well. So this is the fundamental meaning of linear running time complexity, that the running time of the algorithm scales linearly with the input. If we double the input, then the running time will be doubled as well. If we multiply the input by 10, then the running time will be multiplied by 10. Of course, we like linear running time complexity algorithms because they are quite fast and predictable. So that's all about linear running time complexity. Thanks for watching. In this lecture, we are going to talk about quadratic running time complexity algorithms, and we are going to focus on bubble sort algorithm. Bubble sort repeatedly steps through the list or the array or the underlying data structure and compares each pair of adjacent items and swaps them if they are in the wrong order. Unfortunately, bubble sort is too slow and impractical for most problems, even when compared to insertion sort. Insertion sort is another quadratic running time complexity sorting approach, but it is a bit faster. So bubble sort has a worst case and average case running time complexity ortho n squared. This is why bubble sort is not a practical sorting algorithm. We will come to the conclusion that we can do better. We can achieve ortho n log n linear arithmetic running time complexity with heap sort, merge sort, and quick sort. Okay, and by the way, it is not efficient in the case of a reverse ordered collection as well, which means that the underlying data structure is already sorted but in reversed order. Let's suppose that we have a one-dimensional array of unsorted integers 12, 4, -2, 1 up to 11, and of course the aim is to end up with the sorted order. So what do we have to do? We have to start with the beginning and we have to keep comparing adjacent items, and we have to swap the given items if they are in the wrong order. So in this case, for example, 12 is greater than 4, so we have to swap them accordingly. Then we have to keep comparing the items right next to each other, 12 and -2. Of course, 12 is greater than -2, so again we have to swap them. 12 is greater than 1, so we have to swap them. 12 is greater than 3, 12 is greater than 5, 12 is greater than 8. Then 12 is smaller than 56, so in the next iteration we are going to consider 56 and 31. So as you can see, we keep iterating through the array and we keep comparing the adjacent items. Okay, 56 is greater than 31, so we keep swapping the items, and 56 is greater than 11, so we swap the items. And we can come to the conclusion that 56 is the largest item in the dataset. So in every single iteration, we bubble up the largest value to the end of the list. This is why it is called bubble sort. And after every iteration, we keep considering fewer and fewer items. So of course 56 is in its final position, so we don't have to compare it with other items in future iterations. So we start over and keep comparing adjacent items. 4 is greater than -2, so we swap them. 4 is greater than 1, so we swap them. 4 is greater than 3, so we swap them, and so on. 4 is not greater than 5, so we keep going. 5 is not greater than 8, so we keep going. We keep going until we come to the conclusion that 31 is greater than 11. Okay, and again 31 is in its final position. And we start over. -2 is smaller than 1, so we keep going. Okay. And in this case, we can come to the conclusion that 12 is larger than 11, so 12 will be in its sorted position. And as you can see, we keep considering fewer and fewer items. In this case, 11 is in its final position, then 8 is in its final position, then 5, then 4, then 3, then 1, and -2. So this is how we can sort the underlying data structure with the help of bubble sort. It has a quadratic running time complexity, so it doesn't have any practical applications in the main, because we can do better with the help of quicksort, merge sort, or heap sort. Let's take a look at the implementation. First of all, we have to define a method. We have the public static void, and we have the sort method. And of course, we will get a one-dimensional array of integers. These are the numbers we would like to sort. And what do we have to do? First of all, we have to iterate through, starting with 0. I is less than the nums.length, and of course in every iteration we increment I by 1. Then of course we need a nested for loop. Integer j starts with 1. J is less than nums.length minus the I index. And of course, in every single iteration, we increment j by 1. And what do we have to do? We just have to check that if nums at index j minus 1 is greater than nums at index j, it means that we have to swap those items. This is exactly what we have been talking about a few minutes earlier in the theoretical section. So we define a temporary variable which is equals to the nums at j minus 1. Then we have nums j minus 1 which is equals to nums at j index. And of course, finally, we set nums at index j to be the temporary variable. And essentially, that's all about bubble sort. By the way, if you are interested in algorithms, data structures, sorting algorithms, then check out my other courses where we talk about every single sorting algorithm on a one-by-one basis. So as you can see, we have a for loop that scales with the input size. In this case, the input size is the one-dimensional array of integers. We have a nested for loop that scales with the input size as well. Okay, we decrement the input size by the I variable, but anyways, this is going to be quadratic running time complexity. So this is ordo n squared, so n multiplied by n. And of course, the fundamental principle behind bubble sort is that in every single iteration, we set the largest item to be the rightmost item. So for example, if we have a one-dimensional array 2, 4, 1, and 9, and for example 0, then in the first iteration, 9 is going to be at the last position. And of course, we have the 0 here. And then in the next iteration, we are going to consider all the items except for the last one. In the next iteration, we have the largest item, which is 4. This is going to be the rightmost item of the subarray. And in the next iteration, we consider all the items except for the last 2, because these are in their sorted positions. Okay, then we have 2, and then we have 1, and this is the sorted order. So this is the fundamental principle behind bubble sort. Of course, bubble sort has polynomial running time complexity, but it doesn't have any practical applications because we can do better with merge sort, heap sort, or quick sort. But let's take a look whether it is working fine or not. We have numbers, for example, 3, 0, 9, 5, 2, and 1, something like this. Then we call the sort method, as far as the numbers are concerned. And just for demonstration purposes, here we iterate through integer I is 0, I less than nums.length, and of course I++, and we print out system out and println nums at index I. So essentially we iterate through every single item in the one-dimensional array after the sorting operation, and we print out all the values. So we should get the sorted order, as you can see, 0, then 1, 2, 3, 5, and 9, which means that our bubble sort algorithm is working fine. Just for demonstration purposes, we are not going to bother with the result, we just care about the running time. So if we have, for example, a new one-dimensional array of integers, for example with 100,000 items, just for demonstration purposes, we iterate through I is less than numbers.length, and of course I++. We insert the given items to the ith index, so essentially we create a one-dimensional array with every single integer. Okay, maybe it is going to be better to start with the numbers.length and -1, and then we iterate through up to 0, and of course we decrement the value of I, and of course in this case we use 10, 9, 8, 7, 6, 5, and so on. So if we do something like this, I guess it is going to work just fine. So if we save and rerun the application, yeah, it is working fine. What's crucial that let's measure the running time. So we have the system.current time in millis, and after the sorting procedure, let's print out, so system out and println that time taken, and we print out the system current time in millis minus the start. So this is how we measure the running time for the sorting operation. Because we are dealing with quadratic running time complexity, what do we expect? If we multiply the input size by 10, then the running time will be multiplied by 100. If we multiply the input size by 2, so we double the input size, then the running time will be multiplied by 4. So this is the quadratic running time. So if we have, for example, 100,000 items and it takes approximately 1000 milliseconds for bubble sort to finish with the sorting procedure, then what's going to happen if we multiply the input size by 10? So we want to sort 1 million items. What do we expect? That the running time will be multiplied by 100. So if we save and rerun the application, okay, so let's wait for the algorithm to finish with the execution. As you can see, this is exactly why it is not that practical, because we have to wait a lot in order to sort 1 million items. So this is not an efficient sorting algorithm. We can do better with merge sort, quick sort, or heap sort. Anyways, let's wait for it to finish. So far we have approximately 930 milliseconds, and because we have multiplied the input size by 10, we expect to end up with something like this, so 93,000 milliseconds, which is approximately 1.5 minutes. And as you can see, this is working fine. The running time is extremely slow because it has quadratic running time complexity. So if we double the input size, then the running time will be multiplied by 4. If we multiply the input size by 10, then the algorithm will be 100 times slower, and this is exactly what we expect. Okay, so we have 135,000 milliseconds, which means that it takes more than 2 minutes for Java to sort 1 million items with bubble sort. This is why it has no practical applications. Okay, so that's all about bubble sort and ordo n squared, so quadratic running time complexity. We can come to the conclusion that we don't like quadratic running time complexity related approaches because they are too slow to have practical applications. Thanks for watching.